All right, welcome everyone to this video. In the video here, we're going to talk a little bit about mechanisms and just do some more examples of them. Okay, so let's consider the following rate law for the reaction here. Okay, and we're going to use the steady state approximation and the pre-equilibrium approximation to figure out what is that rate law for this mechanism for the reaction 2A plus B going to C plus D. Okay, and so again, for using the pre-equilibrium approximation or the steady state approximation, right, we want to just first start off with the idea of, okay, my rate law is going to be, for the reaction, right, it's going to be related, with either, say, -1/2 times dA dt, right, or right, the minus dB dt, or positive dC dt, or positive d dt, right? All these things equal the overall rate for my reaction, okay? And so I can get my rate law by finding out what are these changes in concentration equal to, right? And I can pick any of these four, right? So I'm going to pick, say, C, right? C only appears in the second equation, right? So I'm going to want to find the rate of my reaction. I'm going to say is going to be related with dC dt, which in this mechanism happens to equal just Kc IA, right? Now the problem is I here is an intermediate, and so we got to get rid of I using things like the steady state approximation or the pre-equilibrium approximation, right, for this mechanism. Okay, so that's right. So what's on this slide is the same no matter what approximation you're using. I've done no approximation so far to get where I'm at, right? To go further, right, to get rid of this intermediate in my rate law expression, that is when I need to use these approximations, okay? So, okay, that previous slide is just summing up what I've just said. So I just kind of skipped over that, okay? And so, right, if we want to use the steady state approximation, right, we're going to assume that change in concentration of I with respect to time is equal to 0. And so when you do that, right, I appears in all three reactions, right, the forward reaction here, the reverse reaction, and then the forward reaction there, okay? So in the forward reaction, okay, I have Kd times A times B. In the reverse reaction, I'm going to have minus K minus D times I times D. And then in the forward direction on the third reaction, it's going to be minus KCIA, right? This is minus V C, minus V minus D plus VD, right? Kind of writing it out like that, right? In the rate law for VC equals KCIA, right? Rate law for VD equals KDID, and the rate law for V minus D is equal to K minus D. This is ID. My apologies, right? And up above here, it's not KDID, it's AB. Okay. Right. Right, and so with that, right, with our steady state approximation, we can then go ahead and solve for I, right? I can do that by factoring out an I in these first two terms, okay, and I'll factor out the minus sign as well to have Kc times A plus Kd times D, or K minus D times D, my apologies, right? That third term stays the same. I can add this second term to the other side, right, to get I Kc A minus Kd D, and that still then just equals KD AB. And then just divide both sides by the KCA plus K minus D, right, to get this final term for what I is, right? And then I'm going to just plug that in to this expression up here, okay? Plug in for what I is up into there, okay? To get this final expression where I would multiply the a's together, just simplify a little bit to get a squared, right? And so this is my final expression, right, for this mechanism, okay? And we see here, right, it's second order in A, sort of, right? Depends on whether or not KCA is much greater than K minus DD, right? But it's first order in B, and then it can depend on D, right? Right, it will depend on D, right? And for large enough product D, right, this will be second order in A, but for you know, the initial rate, when there's no D, this will actually appear first order in A, right? Okay. And then now if I want to do the same question with the pre-equilibrium approximation, right? Again, the pre-equilibrium approximation says in this reaction, right, we're in equilibrium. This is slow, right? This is fast, okay? And so we're in equilibrium, which means the forward rate and reverse rate are equal. So KD AB, which is the forward rate, has to equal the reverse rate of K minus D ID, right? And again, it's called the pre-equilibrium approximation because it's in equilibrium, these are equal, right? And that's, you know, you multiply things over and you see that that gives you this equilibrium constant, right, for the equilibrium reaction, which ends up being KD over K minus D, which equals concentration of I, concentration of D over concentration of A, concentration of B, right? And so, right, that's kind of what I stated before, right? In the previous slide, it's just typed up here, and you just solve for the concentration of I to get this here, and then you're just going to plug that right back in up to the very top. Right, so plugging in up to the top, okay, you know, this into here, right? You'll just simplify to get this expression, right? Which, if you recall, right, the difference between this expression and the other one was that on the denominator here there was a plus K D A term, right? No, KCA, sorry, KCA. Yeah, I was wondering why it didn't seem right in my head, right? KCA, right, was added to that bottom, right? So you see the pre-equilibrium approximation gives somewhat similar results to steady state. Often is the case that steady state is potentially able to cover more cases, more, you know, is more general, if you will, of an approximation than that pre-equilibrium, okay? So this next example here, we're going to look at this simple reaction H2Br plus Br2 forming 2HBr, right? Which we introduced the rate law for this when we first talked about kinetics. Okay, it's a nice example of what looks like a simple reaction, has a much more complicated mechanism with 5 different kind of steps here going on with a bunch of radicals and such involved. Okay, and the question is, right, is you observe that for the rate law, you have a half order of Br2 at very high concentrations of Br2. The question is does that agree with your mechanism? Okay. And we're going to assume steady state approximation. Okay. Now the hint here is asking for saying the rate of the reaction is related with the formation of HBr. Okay. And while it's true, I'm going to do an example here, H2. Okay. Right, because again, the rate of the reaction is equal to minus dH2 dt, which is minus dBr2 dt, and 1/2 dHBr dt, right? these three different things here, right? And I could pick, right, any of these three and I'll get the same answer. Well, if you look, right, H2 only appears in 2 reactions, while HBr appears in 3, and Br2 appears in 3, okay? So you decide, you know what, let's pick H2 here. So the slides have the solutions worked out for picking HBr, okay? And even when you pick HBr, you don't have to follow the procedure I did to solve for the final rate law with the equations that you get, okay? But you could pick HBr, you'll get the same answer, right? You can pick H2 like I'm going to do here, and we'll see that we'll get the same answer, okay? And so, right, the rate of my reaction, right, I'm going to say is minus dH2 dt, which equals, right, the rate of change of H2. It appears in the 2 elementary steps here. In the first elementary step it appears in, it's a reactant. So it's going to be minus V2, right, and then plus V4. Okay. So that's the rate of my reaction I care about. Okay. So to reiterate that, right, the rate of the reaction I'm trying to solve for is factoring the minus signs is V2 minus V4. Okay. Right, and just to write out, right, V1 equals B concentration of Br2 times K1, right? V minus 1 is equal to K minus 1 concentration of Br squared, okay? B2 equals K2 Br H2, right? B3 equals K3 HBr2, and V4 equals K4 HBr H. Okay, right. So you see the rate of my reaction, right, is related to the rate law V2 minus V4. Okay, well V2 and V4 both include our intermediates, right? Our intermediates are H radical and Br radical, right? Those are our 2 intermediates, and so I need to get rid of them, right? And to do so, use a steady state approximation, right? So dH dt, okay? H appears in this V2 as a product, okay? It appears in the third reaction as a reactant, so minus V3, and then it appears in the fourth reaction as a reactant as well, so minus V4. Okay, and that should all add up to give you 0. And the same thing with Br. Okay, we'll do that, right? Br appears as a product in the first reaction. Now 2 of it's being formed, so I'll get 2V1, and then minus 2V minus 1. Okay. Then Br is a reactant in K2 here, right? So sadly, Br appears in every last one of these reactions, right? So it's a reactant in K2, so it's minus V2. Okay, it's a product in K3, so it's going to be plus V3, and then it's a reactant in reaction 4 here, or sorry, product in reaction 4 as well, so plus V4, right? And all that equals 0. Okay. So again, I write things out like this sometimes because it's a little bit easier to see some tricks that we might be able to do, right? Like if I look here, I say, okay, V2 minus V3 minus V4 equals 0. Okay. Right. We'll multiply this entire thing by a minus sign, right? Minus, plus, plus, you know, and then minus 0 is still 0, right? Well, that's minus V2 plus V3 plus V4 equals 0. Well, that is what I have right here. So this chunk of stuff right here equals 0. Okay? Which doing that then tells me, right, that 2V1 minus 2V minus 1 has to equal 0. So that is going to tell me, right, that V1 equals V minus 1. Okay, I get that from this equation down here using the fact that, again, this term up here equals 0, which is the same thing as that term down there. And so then I'm just left with this equation here, right? I'm left with this equation here, which just says 2v1 minus 2v minus 1 equals 0. Okay. So I, that maybe helps, maybe doesn't, right? It does kind of help because now I have, right, I see here, well, using that, v1 equals v minus 1, well, that tells me already some information, right? That tells me then, up here with v1, v minus 1, right, that means I can set k1 br2 equal to k minus 1 br squared, okay? And so I can solve for br in terms of br2, right? Doing that, I can solve for br in terms of br2, okay? And again, right, I guess just kind of see where are we going, where do we have to do, right? We'll plug in for the rate of the reaction up here. V2, right, is K2 Br H2 minus sorry, I was getting ahead of myself, looking at something, K4 HBr H. Okay. And so, yeah, so I still need to know what H is, right? I now know what BR is in terms of BR2. I can simplify that, but I potentially need to know what H is. Okay. And we'll see if we can't solve for that using dH dt here, right? So, okay. So, just, creating a new slide here just to kind of help rewrite some pertinent information, right, than what we've been talking about. So again, the rate of the reaction is V2 minus V4, okay, right? We have dH dt equals V2 minus V3 minus V4, which equals 0, and dBr dt equals 2v1 minus 2v minus 1 minus v2 plus v3 plus v4 equals 0. Okay, and using that stuff, right, we showed that v1 equals v minus 1, which gives us that k1 br2 equals k minus 1 br squared. And so solving for that, you get that br equals k1 over k minus 1 times br2 to the 1/2 power. Okay, so that's what br is. Okay. Now, again, in the last slide, I was like, okay, well, we can plug in for V2 and V4, right? And we see that it's related with BR and H2 and HBr and H, right? Well, I can actually do things a little differently, right? I can also say, okay, V2 minus V4, right? Well, V2 minus V4, using this equation here, right? So using this equation right here, right, we get that V2 minus V4 just equals V3, right? Well, V3 happens to equal H times BR2 times K3. So if I can solve for what H is in terms of BR2 and H2, then I'll be golden, right? And so let's plug in for what dH dt is and see if we can't solve for H, right? So we get K2 BR times H2 minus K3 HBr2 and then minus HBr BR H K4. All that equals 0. And I kind of use two lines here, right? But those things all equal 0, right? So you see here that this term has an H in it, and this term has an H in it. So I'm going to bring those both to the other side. Okay, so I'm going to bring both of those, right? I'm going to add both of those, add both of these onto the other side of the equal sign, okay, to get the equation that K2 BR H2 equals H times K3 BR2 plus K4 HBR. Again, I'm not giving myself a lot of room here, okay? But I factored out the H as well, okay? And yeah, so maybe what I'll do, let's erase some of the stuff down here, okay? And so let's continue on. So let's take this and continue it on down here, okay? So so again, that's K2 BR H2 equals H times the quantity K3 BR2 plus K4 HBR, right? And so with that, okay, we can then solve for H, okay? Right, I can plug in for what BR is in terms of BR2, and I can solve for H, okay? So what I'm actually going to do is go to the next slide, and we're going to kind of copy over, again, some of these equations, right? So we're going to copy over this equation, and then the fact that the rate of a reaction is just equal to V3, right? Using this green equation here, right, I can use this, plug that in up to there to get that the rate of the reaction is just equal to V3. Okay. So again, rate of the reaction equals V3, okay? And then we showed, right, that that BR equals K1 over K minus 1. Yeah, let's do that. Different location here, right? Showed, right, that BR equals K1 over K minus 1, concentration of BR2 to the 1/2 power. Okay? And then the last equation we're at, right, was that K2BR times H2 equals H times quantity K3 BR2 BR2 plus, oh no, wait, or plus here K4 HBR. Okay, and so solving for that, right, we get the H equals K2 BR H2 over K3 plus, times BR2 plus K4 times HBR. Okay, and then plugging in for BR, right? So then taking this equation here and plugging it in here, right? this comes out to be K2 times K1 over K minus 1, the 1/2, times BR2 to the 1/2 times H2, all divided by K3 BR2 plus K4 HBR. Okay. Right, and then V3 here, right, for those who recall or have written down, right, V3 is equal to K3 HBR2. Okay. So plugging that in, finally, the rate of the reaction is going to equal, so plugging in, right, this guy here into H up there, okay, we get that the rate of the reaction is K2, K3 times K1 over K minus 1 to the 1/2, okay, times concentration of H2 here, right, times concentration of BR2. Now it's concentration of BR2 times concentration of BR2 to the 1/2, so this is to the 3/2, all over K3 BR2 plus K4 HBR. Okay. And so this is our lovely final rate expression here. Okay. Now, right, the original problem was saying, okay, at very large concentrations of BR2, this is half order with respect to BR2. Okay. Well, for very large concentrations of BR2, that denominator is just K3 BR2 plus K4 HBR, right? So for very large BR2, that first term is much more important than the second, and so we can approximately just remove that second term, right? And then you're left with, in the denominator, K3 BR2, which one of those BR2s cancels out with one at the top, and you're left with something that's half power in BR2, right? And so this does agree with the experimental observations, okay? Right, and so yeah, and this is kind of your final rate law. And again, so you'll see that you know, doing this in a different way, okay, on the slides, right, you get the exact same answer. And so we'll kind of fast forward through that, right? So again, you know, how I did it is in the slides originally solved for dHBr dt, okay? I had these two differential equations with two unknowns. I used those differential equations to solve for H radical, and then I used some of the differential equations, right, to solve for the Br radical, and in somewhat of a similar way to what we did. Okay, and then I plug in for the Br radical into the H radical solution. Okay, and then I plug that back into my equation up top. Okay, for the H radical, Br radicals. So the thing is right, at this point here, you have, you know, minus V4 plus V3 plus V2, okay? And this can simplify down to 2V3, okay? That using what dH dt equaling 0 gives you can simplify this to 2V3, and so, right, then the rate of the reaction is related with dHBr dt, which, or it's 1/2 dHBr dt, and so you get the rate of the reaction is equal to 2 times 1/2, right, V3, right, and so you get the exact same answer as I did before. Now here, because of how I plugged these guys in up here, right, I get this lovely expression, okay, which requires some common denominators and things like that to simplify things down. But you eventually simplify it down to get this final expression here. Okay. And that final expression, right, gives you the final kind of rate law expression, which here I divided everything by K3 in order to get this expression here where we have this Ka and Kb, which is how I originally presented this rate law earlier on in the semester. Okay. Right. And so again, you can solve these things in multiple different ways, right? Whatever way makes sense to you and works best for you is the way to solve it. Okay. There's no right way, there's no wrong way, there's just the way you happen to have done it. Okay. So just keep that in mind, right, when doing the homework on this first exam with kinetics, right? That the key step is writing out these rate laws, writing out your steady state approximation and those things like that, right? And then the algebra required to get to the final solution, right, can sometimes get a little dicey, a little hairy, but that's not as important as setting all those things up right. If you set all these things up right, you know, most of the time you'll get this right answer, right? Sometimes you'll make a simple algebra mistake, you forget to add something, or you forget a factor 2 somewhere or something like that, right? But that, you know, but that's going to be like a point off or something very minor, right? And so yeah. Okay. So just keep that all in mind, and I hope you enjoyed this video, and hopefully it was informative and helpful to you.